The Big Book of Forces. This is really just the idea of listing some of the forces that you're likely to run into in the mechanics part of this class, and they're just sort of historical names for different types of forces, and I want to make sure we cover them very briefly. The first is weight. The force of attraction by the Earth on an object is called the weight of the object, and if the object has mass m, it has a weight with magnitude m times g, where g is the free fall constant. Being a force, it also has a direction, which is downward. In fact, weight defines downward. The object suffers this force whether or not it is in contact with any other objects. It is the only non-contact force that we will run into in a mechanics class. When we get to electromagnetism, then we'll start talking about some other non-contact forces. They obviously make things more complicated, but right now all we have to worry about is the force of gravity. All other forces we encounter will be contact forces. Obviously, far from the surface of the Earth, this would be modified, as the free fall acceleration would no longer be g, but the weight will be basically m times the free fall constant. We usually represent weight by F sub g for gravity, but sometimes we see W. I don't like it, but we see it. Normal forces. Solid objects have internal molecular forces that tend to resist changes in the shape, specifically to resist the penetration by a different object. We call such a force a normal force. Normal not in the sense of typical, but in the sense of perpendicular, sort of an old-fashioned mathematical use for the word normal. The normal is perpendicular to the tangent. A normal force acts at the point of contact, perpendicularly away from the object in question. We often call normal forces magic, a bit facetiously. Really specifically, they're constraint forces. They get as large as necessary to meet the constraint that two objects don't pierce each other. Of course, real-world objects can't always exert forces as large as they would need to be, so they couldn't produce the normal force that would be necessary, which means the objects would penetrate, meaning you're no longer subject to the constraint of the objects being kept apart. We symbolize a normal force by F sub n. Sometimes people symbolize it with just capital N. Tensions. When a connector like a string or a cord is pulled taut, meaning stretched out, it will exert a force in an attempt to return to its original length. This is called a tension force, or simply a tension. The tension acts in both ends, and an ideal connector is the same everywhere in the connector. We symbolize tensions with F sub t, or sometimes with capital T. Spring force. A special case of tension is the force exerted by a spring or other connector that can stretch appreciably. So normally strings and cords and cables and ropes and all these other things we talk about, these connectors, they don't stretch. They have a fixed length, and when you put them under tension, they'll exert a force, but they won't really get longer. But we know that ultimately this is an idealization, that real things will stretch some small amount. There are objects called springs that stretch noticeable amounts. A Hooke's law spring will exert a force proportional to the amount that it has stretched. That is, F sub s is k times s. Here k is called the spring constant and is measured in newtons per meter. This use of k is very common, so while people use k for other things, often it ends up being used just for the spring constant. Notice that most textbooks would write F sub f as minus ks, so as to say that when you stretch at some distance, it exerts a force back against that stretch, and that's fine, but I like to talk about the magnitude and apply the direction as the problem dictates. Most books will use x for the stretch. I use s, not a big deal. A Hooke's law spring will push outward a reverse tension, if you want, of the same size if it's compressed a distance s. So if you push on a string, it collapses and goes slack, but if you push on a spring, it pushes back and tries to expand back to its original length. The spring force is usually symbolized by F sub s, but since it's like a tension, sometimes by F sub t. Also sometimes F sub s spring, and some other names. Thrust. Thrust is the general term for the force exerted by a rocket or a jet engine. It comes from the expulsion of fluid from a chamber and is the reaction force to it. Thrust is often symbolized by F sub t, which in this case means thrust and not tensions, or sometimes F sub r for rocket. Friction is the resistance of one object in sliding past another. We'll cover friction in much greater detail later in the class. It comes in several varieties and definitely has some subtleties to it. Friction is usually symbolized by F sub little f, but is sometimes symbolized by simply just little f. Drag is a resistive force exerted by a fluid on an object moving through it. It can be very, very complicated, in part because it is generally velocity dependent. Drag usually gives rise to the idea of a terminal speed, and we'll talk about that a little bit later in this chapter. Drag is usually symbolized by F sub d, or sometimes by just d. Electromagnetic forces. Ultimately, all of these forces, except gravity, are just macroscopic expressions of microscopic interactions via the electromagnetic force. Later in the class, we'll discuss explicitly the force between charged objects and the forces between current flows. So right now you don't really have to worry about this, but they are sort of the root causes of the things we're seeing. So when we say like normal forces or tensions, ultimately they're all electromagnetic. And of course, in modern theory, electromagnetism and gravity, we expect to be unified. So really all the forces come down to just that electroweak, strong / gravity force. All right, our next stop will be free body diagrams and how to do analysis of dynamics problems.